Okay, so today we'll start out with just a quick discussion about the final project for the class. I've already put on Canvas Rubric for all the sort of deliverables. So the project is basically an opportunity to apply what you've learned, a lot of the concepts for anyone who's doing a data analysis, I think can help really translate to future research efforts. And so I definitely encourage folks who are working on research related to data analysis to definitely feel free to use some of that as potential project topics. So we'll have a proposal, presentation, and a report. So the proposal will be due on May 5th, which is a couple weeks away. So you have, I think, 2 weeks to work on it. And this is really to get everyone to start thinking about the topic and start exploring potential resources for data to analyze. And then project presentations are going to be happening during the last week of class, so the week before finals. And the project will, the final project report will be due on the Friday at the end of finals week. So for the project proposal, it's basically a short summary, what data you'll be using for the project, what hypothesis do you want to test. I won't go too much into details here. Folks can look over the rubric. I think there should be more than enough detail there, but I'll post these slides as well if anyone wants. Project presentations, we're looking for something like 10 to 15-minute presentations. What did you learn from the data? Interesting tidbits and an overview of the data. And so one of the things that I think is important is that, beyond, applying models and that sort of thing, having a nice sort of summary and overview of the data, providing, summary plots will be an important way to convey sort of understanding of the data set. And then if you have any sort of preliminary results, you can include those in the presentation. The presentation itself won't be kind of the sort of final product, and I'll be giving feedback after the presentation that I would expect for you guys to integrate into the final work. And then the project report. So the process that you took to conduct the analysis, what sort of data cleaning did you do? Thinking about the data overview and how that may have informed your approach. So these are all things that would be sort of worthwhile to include in the report, which will maybe make it a little bit different from your sort of traditional report of just results and that sort of thing. And then, yeah, so really kind of employ the things, employ what you've learned, but you don't need to stretch to every single method that we cover in the course. Make sure that it's really sort of applicable for what you're doing. So, for example, if the data set and problem you're looking at is mainly looking at a discrete like outcome variable, then you want to apply the sort of proper models to that, and you don't need to do sort of every single model that we cover in the course, just for the sake of doing that. Okay, and then some other quick notes. you can partner up for the project, and so folks can work in groups of up to 2 if you want, and obviously the expectation for a group-based project will be slightly higher in terms of length of content and depth of analysis. And then let's see, I'm getting a comment that June 10th is the last day of the quarter. Is that, all right, maybe I have my dates wrong. 1 second.
It seems like the dates might just be a week later.
Oh, wait, so hang on. What's the first day of finals?
I think like June 7th.
Oh, okay. So I think all right. So then I'm gonna have to modify the dates.
It's
then.
June 4th. Sorry.
June 4th is.
Yeah.
That's Friday. June 4th is a Friday.
Correct.
Okay.
Yes, you're right.
Okay. So I will make a note to fix that, and I'll repost the dates. It just means that it'll be sort of 1 week shorter than that. Which shouldn't be a problem for anyone. I'm pretty sure no one started on their projects yet. But so then that would mean that the presentations will be starting on May 31st, and then the final report will be due on the 11th. And let me double check something. So the 31st is also, is that a holiday?
Yeah, it says Memorial Day.
All right. All right, well, I'll figure out the schedule and get back to everyone. This might kind of mess things around a little. We might have some presentations on finals week, but I'll update the dates and let everyone know. Are there any questions about the project otherwise besides the dates?
Is the date for the project proposal going to stay the same?
Yeah, we'll give the same amount of time for that.
Thank you.
Okay. If there are no other questions, so last time I mentioned that we'll be talking today about model selection metrics. And so before we kind of get into that, I wanted to touch back on the sort of central concept about essentially figuring out what sort of model can be used to fit to the data, and this idea about model complexity and overfitting. And so you'll recall our sort of classic example of fitting sort of a line through a bunch of data points. And as we get into multiple regression, right, where we're allowed to look and essentially add more than one variable, you may actually start to see sort of more interesting fits to the data. And so I will actually show, a direct example of this in a second, but you can imagine that, hey, I could fit the data like this or like this, and still sort of in with a linear regression, linear in parameters. And so there's a question of, again, how do we figure out when the sort of fitting becomes too much? So let's go ahead and actually start with the example of this. And let me here. Okay, and so we are going to go back to our patented example again. And we have this set of code, which is, again, generating X's and Y's randomly through a function that looks something like this. Okay, and so hopefully we're all fairly familiar with this. And what we'll do now is to start to add more explanatory variables. And one simple way of doing this is actually sort of adding exponentiated explanatory variables. I'll describe what that means in a second. So let's have an x2, which is just x squared, and then we'll have an x3, which is x cubed. And let's observe how the model changes as we increase complexity. So when I say increasing complexity, essentially what that means is I'm adding more explanatory variables into the model. So our first model, right, is just y on x. Then we'll do y on x plus x2. And then we'll do a third model of y on x plus x2 plus x3. So let's go ahead and run these and see what happens. Oh, I didn't run my x2 and x3 yet. There we go. So the first model we're pretty familiar with. We've seen this before, right? So intercept here, not statistically significant, which makes sense given that we don't have an intercept in our original one. And then a coefficient sort of close to 0.5. So let's take a look at what happens as I add even more explanatory variables. Okay, so things start to change a little bit, but one thing that I'll kind of point your eye to is the R squared value. So here it's 0.34, and here it's 0.349. So one of the things that you should sort of keep in mind is that as I add more and more variables, so we'll forget for a second about whether or not they're significant or anything like that. But as you add more variables, you are capturing sort of more and more variation, right? Because anything in addition to what you've already added is simply, coincidentally going to be able to capture some of the variation in the way the points are outlined. And so we can see this happening as well for model 3, just slightly higher R squared value. And so, we can see that it may not necessarily be kind of the best metric for deciding kind of what variables to put in, because really at the end of the day, if we were going by R squared to decide what variables to include in the model, it would always just tell you to put as many variables as possible. And so let's take a look at a sort of more extreme case of this. So what we're going to do is we're going to generate a data frame that essentially is doing this, but it's going to run for all explanatory variables from exponentiated variables from x to the first power all the way up to x to the 50th power. So the way we'll do this is we'll make a data frame with our first y, and then we'll do a for loop, and we're going to essentially add in we're going to add in another variable or another data frame that's going to be x to the n power, and you're going to just go from 1 through 50, and the name of each one is just going to be x. Oops, sorry about that. I can just do this. So paste is a way of putting strings together. So this is just saying put the x and the n, and then if you have paste 0, you can normally specify how you want to separate the strings that are getting put together. With 0, you're just saying don't put anything in between. And then we're going to cbind, which is a column bind, the y's. And so to give you a sense of what this looks like, or what this code is doing, I'll just draw it out really quick. So we start with a y, and let's just say, A, B, C, and then we'll start with x to the first power, and it's going to generate this and then add it here, so that on the next step we'll have x1, A, B, C, 1, 2, 3. It's going to generate x2, which is going to be 1, 4, 9, and that's going to add that onto there. And then, right, so the next step will be something like this. And then it's going to make x3 and add it onto there until we have a table with 50 of them. So that's what this code is doing here. So I'll go ahead and run this. I'm going to do, so actually I'll just sort of copy and paste this over. So this line of code, or these couple lines of code, is going to be doing a similar type of thing, except it is going to be predicting. It's going to be creating a data frame that I need to use for the predict function. And so this is essentially going to be creating a testing set that I'll be that I can compare against my model. And so if you'll recall from last time, this is one of the things where we're going to be able to look at out of sample validation to see how well the model does as you make it sort of more and more complex. Okay. Oop. Okay. So creating a test set and then putting it into a data frame. So this is again sort of going creating the same thing from before that I was describing, and I'm actually just going to go ahead and show you guys what the result is, or what the sort of point of this example is. So I'm adding there's a couple more sort of lines of code. A lot of this is repeat of what we've seen before. This is actually a way of doing the cross validation, and I'm gonna kind of skip ahead to this, and I would encourage you guys to look at this in the notes once it gets posted. But let's see. Uh-oh, hang on. Oh, I have to run all of this. Okay. We'll have a sort of new plot window. Hang on. Where did it go? Oh, here we go. Okay, so we may have to wait for this to pop up. Does not appear to be plotting for some reason. All right, hang on. Okay. Kind of wanted to pop this out. Okay, well, it's not updating that much, but that's okay. So, now here we go. So what is happening here? So this is the same set of points, and all of this is describing sort of 50 different models where I have, for one, it's just y is a function of beta times x1. For this one, it's y is a function of beta x1 plus beta 2 x squared. And then this one includes the cubic term, and to the 4th power, 5th power, and so on. And so what you'll see is that as I include more and more explanatory variables and terms, the line starts to get a little bit more sort of squiggly and kind of like nonlinear. And this kind of principle is actually going to be one of the ways that we'll start to explore nonlinear models. But the sort of main takeaway here is that having that extra variation may not actually be necessarily improving the model, right? So even though, you know, in theory, the R squared is improving as I add more and more explanatory variables, if we look at other metrics to consider whether or not the model is doing a good job, you'll actually see that it starts doing more and more poorly as you add more explanatory variables. And that has to do with this concept known as overfitting, which we'll talk about in a second. If I actually just do one more plot, let's see. So this is going to be the same thing, but now it's actually going to give a metric for the out of sample mean squared error. So this is doing kind of like a procedure similar to the k-fold validation that we were talking about before. We have an in-sample mean squared error. So that is this term here in the top left. It tells you the average size of the error fit to the points. And you can see that the in-sample mean squared error, that is the data you trained it on, because you're training it on, you know, those existing points, you're going to get a better and better sort of improvement in your in-sample mean squared error as I go from a less complex to a more complex model. But if I kind of rely on taking out this test set that you didn't train it on, but we know is kind of representative of the true function, you'll actually see that, okay, as we add a little bit more, the mean squared error goes down, but then at a certain point, it'll start to go back up. So, you know, here we get all the way down to 163, but as you go sort of further and further, it starts to increase again. And that again has to do with the fact that you are essentially overfitting your data. Okay. So let's talk about this a little bit more generally. Unless there are any questions. All right. So the whole idea is that, again, if I have some points, and I draw a line, so we can create a better fit by adding more variables or changing the functional form. But if I do something where I kind of better fit my points, if I happen to sort of generate more points via a sort of new function or via having held points back as a sort of testing set, you know, suddenly the model will perform poorly. Right. So adding points. So there is a concept known as the bias variance trade-off, which is essentially the central premise behind a lot of, you know, why this happens. So the sort of best analogy that I use for this, so if we've got some like target rings, you can have low variance, low bias, high bias with low variance, and then low bias with high variance, and high bias with high variance. And you may have seen something like this to describe, you know, difference between accuracy and precision. So it's essentially a very sort of similar concept. So when you have low variance and low bias, it means you're hitting your target sort of right where it needs to be. When you have high variance but low bias, it means that you are sort of accurate, but that your points may be really spread out. If you have high bias and low variance, it means that your precision is high, but your accuracy could be low. So you might see like a tight grouping like this, right? And then if you have high variance and high bias, then you both have like a big spread, and it's not very accurate. So in this idea, we see kind of a similar principle. So when thinking about the error of a particular model, so I'll write out kind of the mathematical notation. But again, this isn't something that you would need to memorize. This is more kind of for your reference. So we talk about the error, right, as so this would be your y hat equivalent, but it's often kind of written like this. And this can actually be expanded to look something like this. So the error of your predicted minus actual squared plus the expected value of your predicted minus expected value let's see, do I have, I think I have too many parentheses. Okay, but a sort of broken down version of this is essentially like this. So bias squared, variance, and noise. So these are essentially the broken down components of your error term. And when you have overfitting, so this is when we have a lot of sort of model complexity. You worry about the variance being too high. And then when you have underfitting, the bias is too high. So thinking back to the example that I just showed, when we try and figure out which of the x1 all the way to x to the 50th power and how many sort of variables to include, it is really like the best model that you can devise is essentially one that accommodates the trade-off between your bias and your variance. And so we can think of this in general terms of model complexity. And so this can be thought of as the sort of number of explanatory variables that you might have, or how complex the functional form of the model is, once we start to depart from linearity. And how this relates to our error. And as you increase your model complexity, right, we get our model fit, that line that goes through the points, right, gets closer and closer to the observed points, and in that way you are decreasing your bias as you increase your model complexity. And so that error term will shrink as you add more variables or make your model sort of have a functional form that gets essentially fitting closer and closer to the points. But as this happens, you will also increase your variance. And so what you want is, so you'll have this line, which represents your total error, which is going to be, variance plus bias. And so really what you want is to find this point here. And you want to be able to balance the complexity of your model in such a way that you are kind of decreasing your bias as much as possible, as well as your variance. so that your total error is kind of minimized. And so this is the kind of point that essentially you would try and find through something like a cross-validation procedure, and through some of the other metrics that we're going to talk about today. It's all sort of meant to kind of hone in on this concept, this idea. Why don't we actually take a quick break here? I think this is a good point to stop before we start talking about our model selection criteria. And in the meantime, if anyone has any questions about this, happy to chat. Otherwise, let's break until 2:57.
Hi, Alan.
Hi, Hanif.
Yeah, I have a quick question about the cross-validation.
Yeah.
Our cross-validation data set should change in every epoch, or it should be constant for many epochs. I think if we can change it in every epoch, we can increase our accuracy, yes?
You're talking about when you like update the when you update the like variable selection.
Yes.
Yeah. So we haven't really talked too much about that yet. So when you are separating out the like test sets with the way that we've talked about cross-validation, I think that as long as the sort of procedure is consistent, the variation that you get from doing each set of cross validations should be kind of robust enough. If it's like really close, then you could randomly select again, but we aren't quite at the point where we're talking about these epochs where you're essentially doing sort of new new variable selection, if that makes sense.
Thank you.
All right, so let's continue on and talk about model selection. So again, this is the task of selecting a statistical model from a set of candidate models. And so suppose we have data for y, x1, x2, dot, 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 x to the n. There's a question of which model is best, right? And so we could have a whole slew of models here. We could have y equals beta 1, x1 plus, or not plus, versus y equals beta 2, x2 versus, you know, all the way out. And then sort of in more dimensions, we can think about y equals beta 1, x1 plus beta 2, x2 versus y equals beta 1, x1 plus beta 3, x3, and so on and so forth, all the way until you have, oopsies, y equals beta 1, x1 plus beta 2, x2 plus dot, 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 all the way until you have beta n, xn. And so we had mentioned this before, and the complexity of having n number of variables means that you have sort of on the order of 2 to the n combinations. And so we need to think about some efficient ways, essentially, figuring out what variables to include in there. But before we talk about some of the algorithms that will help us do model selection, we need to talk about the criteria for which, under which you can use to evaluate, you know, which of any sort of particular model might be the best one, right? And so the way that one of the ones that we've talked about, right, is to do a cross-validation procedure, which is common for certain types of models. Other criteria we've seen don't really work very well. So like the R squared, we see that if for example, that I were to use R squared as the criteria for selecting a model, I could tell you that this one is the one that it would choose always, because the most complex model will essentially capture the most variation. So we don't want to use that. And so let's talk about some of the alternative criteria. So common criteria for model selection. So the first one we'll talk about is the Akaki. Actually, I don't even know how to pronounce pronounce it. It's the AIC, Akaki Information Criterion. I think that might be how you pronounce it. So this is an estimator of the relative quality of statistical information, and generally the smaller is better. So the equation looks something like this: 2k minus 2 ln. So this k is the number of parameters, and this L hat is the maximum likelihood value. So don't worry too much about kind of the theoretical nature of this. But the important concept to understand, right, is that it is essentially a balancing act between model complexity, right, number of parameters, and then how well it's predicting. So this is sort of qualitatively a way in which we are getting at this sort of this bias variance trade-off, right? And so I can increase the number of parameters, which will cause the AIC value to go up, right? And that's actually not what we want. And so that is acting essentially like a penalty value, so that yes, I can actually improve my likelihood, my maximum likelihood value by increasing the number of parameters, but that comes at a cost as defined in the AIC. And so most of the criteria that we're going to talk about now is essentially a sort of reflection of this. So you can actually simplify this for specifically a linear model. The linear model form of this looks like this: RSS plus 2 so this is the AIC for linear models. Okay. So that is one common form. Another is known as Mallow's CP. So this reduces the RSS. 1 second. Reduces the residual sum of squares while taking into account the number of parameters. So this is oops. This is proportionally equivalent to the AIC for linear regression. So it's actually very similar in structure. So CP is equal to 1 over n. So this is sample size times RSS plus 2k this. So residual sum of squares. This is number of predictors. And this is the estimate of your variance. So proportionally, it's going to be essentially equivalent to the AIC. This is another sort of common criteria that folks use. And lastly, we have the Bayesian information criterion, also known as the BIC. So also similar to AIC, but with a different penalty for parameters. So BIC is going to be equal to the log of n times k minus 2 ln of your likelihood. And so you'll notice that the form of it is quite similar. And for linear models, it'll look something like this. So this is better, again, better if smaller, and then bigger penalty on models with more variables. And I'll talk about differences between these different criteria in a second. And when you sort of use one versus the other, although sort of taking a step back and thinking of these more generically, yeah, generally it's a good idea to kind of look at a couple of these. You'll probably find that that the exact model might be slightly different, that if you were kind of trying to minimize the AIC versus the BIC. But sort of all of that having been said, these are all essentially trying to do a similar type of thing, right? Which is, again, to minimize this bias variance trade-off in different ways. And without sort of having to go through the complexity of necessarily doing a full-on sort of cross-validation. Although, again, that is one of the ways that you can do in addition to what I'm showing here. Okay, and the last one that I'll talk about is the adjusted R squared. So adjusted R squared is equal to 1 minus RSS minus TSS. Okay, and so this right here is the same as we've seen before, but there's an extra term here, n minus 1 and minus k minus 1, which essentially penalizes the model for having too many variables, right? And so R squared is between 0 and 1 and bigger. So unlike the AIC, the MalloCP, and the BIC, in this case, bigger is better. And so when the number of parameters increases, so several steps here, right? So as k increases, your denominator decreases. So actually, let's do it like this. As k goes up, n minus k minus 1 goes down, which means n minus 1 over n minus k minus 1 goes up, right? Because you're dividing by a smaller number, which means that 1 minus, that whole term will go down. So in other words, as k increases, your adjusted R squared decreases. So now it is equivalent to, well, not equivalent, but it's the same principle as R squared, but now you have a penalty term for having essentially too many variables. And again, the concept being that you want to try and have some kind of term that penalizes the increase in variance, in the sort of variance contributing to the error, as you add more and more variables. Okay. Any questions? So the R squared tells you how well does the model explain observed data, whereas your AIC, MalloCP, and BIC, how well will your model fit new data? And lower means better prediction. Oh, and I should put adjusted here. And the important thing to note is that both, or all sets, or all criteria, we'll call them, criteria penalize having more parameters. Okay, and that again is relating to this idea that you will start to increase the error term from variance as I add more parameters into the model. So AIC, CP versus BIC. BIC is argued to identify true model as n approaches infinity. So typically, when you have a larger and larger data sets, if you have more observations, because the BIC includes this additional term about how the fit kind of relates to that. You know, you have the ln, the log n term. It's sort of accommodating the fact that it has more observations to look at, and therefore we typically consider the BIC better for models with sort of larger numbers of observations. But AIC minimizes selecting a quote unquote bad model with small n. So if you have a smaller number of observations, the AIC can sort of functionally perform a little bit better because it doesn't have to sort of balance out that initial term against the number of observations. And then the last thing that I'll mention in relation to this is that you always have the option of doing the sort of cross-validation procedure, right? And in that case, the criteria is going to be the mean squared error, but it's going to be the out-of-sample mean squared error. And that inherently takes into account sort of empirically the increase in error, right? As you add more parameters, because that's actually directly what you're measuring in the cross-validation. It takes the mean squared error of sort of new values or new testing values for the model. So, you know, I would argue that cross-validation is probably the most direct way of doing this criteria selection. But it's also probably a little bit more complex, as opposed to being able to kind of just plug into these things. And cross-validation can also be a lot more computationally complex as you're getting to sort of larger and larger data sets. Whereas these ones are going to be sort of really nice approximations of your sort of bias variance trade-off without having to get into that level of complexity. Okay. Let's see, how much time do we have? Okay, we've got plenty of time. So let's now think about, so we now have a whole set of different criteria that we can now employ to measure the quality of models against each other. And as I was mentioning, you have 2 to the k, essentially, or 2 to the n number of possible combinations of variables for, you know, when you have sort of n or k number of parameters. So we need to come up with a we need to come up with a way of sort of efficiently being able to decide what variables to include in the model, even kind of before we think about measuring the relative quality of them through the criteria that we've discussed. So one of the most common and straightforward versions of doing model selection is known as stepwise regression. And so this is a technique of adding / subtracting one variable at a time into the model. So we're going to talk about the sort of two classic ways. So there's forward stepwise selection, and there's backward stepwise selection. And we'll talk about how to do each of these in turn. So I think actually the best way to kind of describe the algorithm is essentially just to kind of walk through it. Okay, so the first step, choose a model with no predictors. For k equals 0 to total number of predictors k. So you can actually almost think of this as like a for loop, right? In R, which is essentially what it is. So we're going to add one additional predictor test all different remaining predictors. Actually, let me write this a little bit more clearly. Well, add one additional predictor at a time. Test each of these models with the one new predictor. And then select the best additional predictor. And when we say best, we have to use one of the criterion. And so this is either your adjusted R squared. Oh, sorry, no. So this one actually we typically, so within the steps, because you're actually using the same number of predictors, you could actually just go ahead and use the R squared or the RSS. And then once you've gone through all of this, you select the best overall based on selection criteria. Okay, and this could be your adjusted R squared or your AIC or your BIC. So let's show a sort of rough walkthrough of this before we show an implementation in R. So let's say you've got your Y, your X1, your X2, and X3. So in step 2A, what I'm going to do is I'm going to look at Y equals beta 1 X1, Y equals beta 2 X2, Y equals beta 3 X3. And then we'll take a look at the R squared. So let's say R squared equals 0.9, R squared equals 0.95, R squared equals 0.85. So then you select this model. So this would be step 2B. Actually, was that step 2B or 2C? 1 second. We have add one additional predictor at a time, test each one of the models. Yeah. So that's 2B, and then this part is 2C, where we select this one. And then we repeat. So we have 2A again, but now we're starting with Y equals beta squared X squared. And then we're going to add in one more parameter. So this one's going to be beta 1 X1, Y equals beta 2 X2. So in this case, these are the new ones that we're adding. And in this case, we're adding this one as the new variable. And actually, probably shouldn't use beta here. Let's do alpha like this. So step 2B, we'll have R squared. So maybe this will be 0.96, and this will be 0.97. So then in step 2C, we're going to select this one. And lastly, we will do repeat again. So now I have Y equals something like this. And you've added this in. You probably technically don't need to do this part since there's only one of them, but for consistency, we'll do that. And the very last step in all of this is going to be, oh, I see a question.
If you wanted to finish first, it can definitely wait until you finish your example.
Wait, sorry, you cut out for a second, go ahead.
Yeah, it's kind of a general question. So if you wanted to finish your example first, then I can ask afterward.
Oh, okay, yeah, sure. Yeah, let me do that. Okay, so the last step, so step 3 is I'm going to look at I'm going to look at my criteria for each of my quote unquote best models. So this could be AIC equal to, you know, let's say this is 0.3. Let's say this is AIC equals 0.2. And let's say this is AIC equal 0.25. And so in this case, we've decided that this model is the best one. And so this is, right, the kind of procedure where, right, I go and add one variable at a time, look at all the R squareds, pick out the best one, and then you could then move on to your next step, add another variable, pick the best one, move to the next step, add another variable. And then you go back and you look at your final model criteria selection via, you know, your AIC, BIC, or adjusted R squared, and pick the best one. There's a presumption in this case that each of the steps will progressively make them better, which is not always true. And so that is one of the weaknesses of a model like this. You'll notice actually, if you're looking carefully, that we've looked at a total of 1, 2, 3, 4, 5, 6 models. But in fact, we should have 2 to the 3, which should be 8 models. And that is the power, that's one of the strengths of the stepwise regression, is it doesn't need to look at all of them. It cuts out certain combinations of variables based off of the selection process. And so whereas ordinarily the combinations would scale exponentially, the stepwise regression will scale linearly. But it also means that I never get to look at, for example, I never get to look at the combination of beta 1 x1 plus beta 3 x3, right? This is never in any of the possibilities, because in the first step we said that beta 2 x2 is the sort of best one, and so all subsequent steps include combinations with beta 2 x2, and so this one would be omitted. So that's one thing to kind of keep in mind when you do this stepwise regression. Okay.
Could I just ask something before you move on to the next slide?
Yes, yeah.
I didn't get the last 2A step that you did. Like it's gamma 1 x2 plus gamma 3 x3 and then gamma 2 x2 again.
Oh, sorry. Sorry, it should be x1, right? Yeah, x1. Yeah, my bad. Okay, Sarah, do you want to ask your question?
Yeah, thank you. So I've read some criticisms before of stepwise regression, and kind of my impression of the criticisms was that similar to conversations we've had before, where if you use a method like this, it doesn't necessarily require your intuition to fit the model that includes most important variables based on, say, like your professional knowledge.
Yep.
So I guess kind of my question is that one of the, am I accurate first, I guess, and that being my impression of the weakness of using a stepwise regression? And then as kind of a secondary component to that, if I input only variables that I do think intuitively are important to this model, does that compensate for that? Like, just because I'm not necessarily putting intuition into exactly which variables end up, I am using my intuition to select the set of variables that I think are important.
Yeah, that's a really important question in regards to this type of thing. And actually, to a degree, I do agree with that. Oh, it looks like I cannot create any more whiteboards. Okay, so we're gonna go back here and clear this. Yeah, so part of it actually has to do with the fact that people often so I've heard this criticism too, and I do agree with it in some ways. And I think the most common mistake that I think exacerbates that exact point is that people will often do the wrong type of criteria for stepwise. So one of the most common ones that I've seen, and actually have seen, I think I've been taught this in a class before, is where you do stepwise with p-value as a criteria. Okay, so first of all, don't do this. So we think about, I think when we're talking about the selection of variables that and sort of departing from your intuition about whether or not variables should be included, I think this one is particularly egregious because essentially what you're saying is that as long as it has sort of statistical significance, then you are deciding whether or not to sort of include it in the model, sort of regardless of kind of what it does for the model, if that makes any sense. Because you can have variables that help capture some of the essential like bias or variation, and can help with your prediction without necessarily being significant. And so when you do stepwise regression with this procedure, yeah, it is this idea of sort of kind of taking your intuition away from selecting variables, and so that is also, I guess, somewhat true for, you know, using the criterion that I mentioned, like the AIC BIC adjusted R squared. But in that case, there is some kind of like statistical reasoning for why you would do that, right? So it improves your ability to do prediction and importantly out of sample prediction, and it's sort of trying to minimize this bias variance trade-off idea, which if you were to do p-value as like criteria, it would not do any of this. And so to a degree, statistically, it makes a lot more sense than this particular sort of no. And then in terms of in terms of like taking the sort of intuition out of it, I think that part of it also needs to be present in your sort of variable selection decision making, and certainly, you know, that the statistical justification doesn't necessarily mean that that it's a good idea to select those variables. And so when you're talking about, okay, making an initial set of variables to choose from, because that's kind of the intuition for, you know, why I think there might be something going on with the relationship between the y's and x's. Yeah, I think that that is definitely a legitimate approach, especially as an initial way of like paring down the sort of data. You can certainly run into examples where like your x's may have nothing to do with the y's, and so like from a qualitative standpoint, like it doesn't make sort of much sense, and so you can always kind of use your judgment there when in sort of coupled with the stepwise regression. So I think it is a really important point to consider, that just because you're doing stepwise regression doesn't mean you need to sort of depart from your intuition about how the relationships occur. That having been said, it also goes the other way though too, right? Because some of these approaches, like the stepwise, may point to relationships that you might not have thought to occur in the first place. And so it can actually reveal things to help move away from initial biases you may have about the data. So that type of effect that you're talking about can definitely go both ways. So it's important to think about it in that context too, right? So you could kind of discover a new relationship that you might not have thought otherwise. You know, that's one kind of way to view it, or you could view it as it doesn't really kind of make sense at all. And that's where kind of your own kind of judgment and interpretation come into it. Okay, I see another question. So what if we have like hundreds of variables? Yeah, so let me clear this again. So let's say we were to do a stepwise regression with from x1 all the way to x100. So the way this would work is that in that loop, right, we would have, you know, first loop, we would test 100 models, right? You have x1, beta 1, x1, you've got beta 2, x2, beta 3, x3, and so on. So there's 100 models in the first loop. In the second loop, we would have to test 99 models, right? And so on and so forth, until the 100th loop, you would test one model, right? Because and so it would be the number of models that you would have to test would look something like this in a stepwise regression. And the big benefit of this is that this number is substantially smaller than 2 to the 100, right? This this is going to be less than, wait, is that right? It would be, this would be less than 100 squared, whereas this would be, you know, more than the number of molecules in the observable universe. So you can see how stepwise regression becomes extraordinarily efficient at testing combinations of models across sort of a large domain. But again, it is doing it at the cost of omitting lots of different combinations. So that is important to consider. The other one that I mentioned is backward stepwise selection. So this is same as forward selection, but start with a model with all predictors and remove one at a time instead of adding. So in this case, you know, we would do something like in the example that I gave, it would be beta 1 x1 plus beta 2 x2 plus beta 3 x3. And then you would then test y equals beta 1 x1 plus beta 2 x2, y equals beta 1 x1 plus beta 3 x3 versus y equals beta 2 x2 plus beta 3 x3, right? So we are subtracting one away each time. We'll look at the r squared for each of these, select the smallest one, and then you'll do y equals beta 2 x2, y equals beta 3 x3, and then you'll do a comparison of your AIC, BIC, adjusted R squared. So it's exactly the same in principle, but we're going from everything to nothing as opposed to from nothing to all the parameters.
Can I ask another question?
Yep.
So can you talk a little bit about, like, when we're using stepwise regression, should we still split the data into training data and test data? Or since this is kind of a streamlined process, is it better to just fit the model to all of the data, but then we miss out on like the out sample?
Yeah. Yeah, good question. So you can, I generally, the way that I would do it would be on this final step. If you wanted to do like a real out of sample validation, you could do cross validation to select the final model as opposed to using AIC, BIC, or adjusted R squared. In theory, you could do it as you move through each of the models. So you could look at the out of sample MSE here and here, right, and here. But in that case, well, in that case, you would literally just choose whichever one came out the smallest as you move through all of your models. It's kind of like skipping some steps, but you would also need to do this probably many times, right? As opposed to here, you would only need to do it three times. In this case, I'd need to do it I would need to do it, what, 6 times? And the reason why you wouldn't just do it like that is typically, you know, as you get to sort of larger and larger models, the cross-validation process itself can be a little bit computationally intensive, right? Because you're doing this like sampling procedure and then testing it, or training it and then testing it against every single model for a k number of times for however many folds that you're doing in your k-fold validation. And it would be, I think it would be fairly unusual. I mean, it's definitely possible, but I think it would be fairly unusual to arrive at a different answer than what you would get if you did it the sort of regular procedure. And so I think that's why people do it that way. It's just slightly more efficient. But there's nothing wrong with doing the out of sample mean squared error for everything. That, I mean, procedurally that would be totally fine. But efficiency, from an efficiency standpoint, it would be a little bit more intensive. Okay, so let's see here. Why don't we actually end a little bit earlier today? I think that I wouldn't have time to sort of carefully walk through all of the code for implementing the step forward regression. So so we'll start with that next time. Yeah, and so next time we'll we've just started to cover one particular algorithm for doing model selection, via stepwise selection. And so we'll show how that's implemented next class. And then we'll talk about a couple other sort of newer procedures for doing model selection that are actually commonly employed in fields like machine learning. Okay, so we'll end here, and I'll stick around a couple minutes if anyone has any questions on the lecture materials or on projects or even homework if folks have looked at it. And just as a quick aside, so the homeworks have been posted, so or homework 2 as of today, and it will be due next Wednesday.
I had a really basic question. So I was trying to knit my R markdown as a PDF, and it just turns out as gibberish. I think maybe do you have to download another software for that, or?
Yeah, so I'll just say that I'm not super fluent in doing knitting in RStudio, but one thing to know is that you have to have like a specific like format for your code. I can't sort of quite recall exactly how it's supposed to look, but I can send you some tutorials on the structure of the code that gets knit, and then yeah, if hopefully that would solve the issue, but if not, we can chat more.
Yeah, that'll be great. And also I noticed you upload your notes as a text file, which also I cannot read. It opens up in Notes. Again, I'm assuming there's a software that I'm missing here.
Oh, no, so, okay, hang on. One moment. Um, so is this what you're talking about here? Can you see my screen?
Yeah, 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 yeah. That.
Yeah. Okay, so there should always be a PDF file that looks like this. So I'm not sure if this is what you're talking about, but the PDF file you should always be able to kind of read.
Right. Yeah, that's readable. That I can read.
Yeah, so that is the set of notes, and I think I had mentioned at the beginning of class about LaTeX, which is a type of word processing. So instead of like Microsoft Office, Microsoft Word, you can actually do Word document generation programmatically. And so I think some folks were interested in learning about that. So I said that I would include the code that I would use to generate this PDF. And so that is what this tech file is. And I may not be able to, okay, but so if you, so I can just show you, so this here is how I create that PDF file. You don't actually need this because it's exactly the same as the PDF, but if you're interested in learning LaTeX and the structure of it, you can always kind of look at this. And it's kind of the reference point for creating the PDF. But this is how I actually compile the notes. So if I run this, it's be, you should see in a second. It'll pop up somewhere.
So this is also basically, so this is in LaTeX, not in our studio.
Yeah, exactly. I don't know why the PDF isn't showing up. Hang on. Nope. Yeah, usually it pops up, but okay. When this runs, it'll open a file that looks like this. 1 second. Yeah. So you can see here, right, like TTP 289, lecture 6, TTP 289. Yeah, and so this is how I create this PDF file. And in terms of opening it, if you want to look at it, you can open it with any generic like notepad, or if you have LaTeX, they have some like software that handles this. Yeah.
Right, thank you. So just to be sure, whatever you write on the whiteboard during classes, that's only in the videos. It's not in any of the notes, right?
Yeah, so all the stuff that I'm writing down, I don't know of a way of like saving it, but all of that written material is based off of these PDF notes, and actually the PDF notes should hopefully be a little bit more thorough, hopefully. And so I actually kind of look at all of my handwritten notes and then write it into the PDF notes.
I see. Thank you. Thanks for
Yep.
clearing that up.
I have a question on the AIC and BIC. So how does it tell how well your model fits new data without having like the out of sample validation, or is it the same thing?
No, it's not, and it's a little different. So because it's using a maximum likelihood estimator, that is kind of its estimate of how well predictions are going to go using a particular model. So it is not actually doing like true out of sample comparison. It is a proxy for doing that. But I think importantly, the fundamental difference between like the ASA BIC versus like an R squared, right, is that the metric itself is meant to capture the prediction error essentially, right, through the maximum likelihood, as opposed to your R squared, which is doing this like TSS RSS ratio to look at something different, right? It's looking at the variance that's being captured, which is not the same. And so most people consider AIC BIC to be some like proxy for a model's ability to do out of sample prediction, like as a proxy for the measure of how well it would do, but it's not the same, and may not necessarily be the sort of best. It wouldn't actually represent that in reality all of the time, but it's kind of a shortcut for doing it without actually doing the out of sample procedure.
Okay, got it. Thank you.
Yeah.
I want to ask a question. So just want to make sure. So out of these four, we only need to like satisfy one criteria out of four, right? Or do we have to check everything?
Oh, yeah. So, I mean, it's you usually. I mean, most people usually just select one. But actually, even on the homework, I think I asked to check different metrics. And in practice, it's kind of good to do that sometimes. You could actually get slightly different answers if you do AIC versus BIC, for example. And then the other thing, and probably more importantly to keep in mind, is that you can think about when it makes sense to apply one type of criteria versus another. When I was mentioning, if you're particularly, if you want to represent the model that best captures the variation, then you do the R squared. If you want, the thing that does the best predictions, then you might want the AIC or BIC. And then depending on the sample size, you might choose the AIC or BIC. And so, yeah, at the end of the day, you really just kind of need one, and you want to pick the one that kind of best suits your needs. But usually, it's good practice to maybe take a look at a couple different criteria and see if the models do align. And if not, like, you can think about what the reasons might be that they're not the same. Yeah, and so it's kind of like up to your own judgment, but there's definitely the common practice is to use, you know, one particular criteria.
All right. And here and in the whiteboard before you write the how well will your model fit new data. New data means the prediction, or
Sorry, what was that?
you wrote there like how well will your model fit the new data. New what new data here?
That's kind of more in theory, like because the AIC-BIC is meant to get an estimate of its ability to do prediction. It you know, kind of assuming that you would do sort of out of sample prediction. You're not actually doing it with new data, but it is a proxy or an estimate of how well the model might fit new data compared to other models where you've run the AIC-BIC.
All right, thank you.
Yep.
I have another question about stepwise regression.
Yeah.
And you might have said this, I'm sorry if I missed it, but is it possible to use stepwise regression if I'm also interested in including like an interaction term, or I would introduce a variable like in its nonlinear form?
Yes. It's definitely more tricky when you get to that because the the interaction variables will also increase the number of combinations. And so I don't know of like a great automatic procedure of doing this interaction to do these like nonlinear variables together. In practice, I guess when I've seen it being done, it's always like based off of intuition and just including it into the set of variables that you're gonna step through. And yeah, I would say that's probably the I guess quote unquote best way. I mean, if there is a best way, you can probably be like overly like liberal with the number of like interactions because the procedure is fairly efficient. So you could just like throw in any sort of suspect number of interaction terms that you think might have an effect. And this kind of goes back to what you're saying before about like using your intuition as the first kind of slice of variables to include in the set to do stepwise regression on. And so it's I would kind of go along the same lines as anything that you suspect might be interesting based on your intuition and knowledge of the data. Yeah, just throw it in and see what happens. Yeah, other than that, like if we think about like you couldn't actually do an approach that does stepwise combinations of variables in the same procedure, right? Because I think that would cause it to grow exponentially again with the number of variables, because with each one you now have, yeah, that's right, because with each variable you would if you were to treat it in a stepwise manner and you were to do them sort of one at a time, but you'd have all the combinations, you would now grow at n squared as opposed to n. Yeah, so I don't think that would be the stepwise procedure would be a way to do the combinations of interactions.
That makes sense. It also seems like that would have the potential to select an interaction term that was not totally reasonable.
Yep. And actually, you know, that actually when I think about it as well, you start to get into some dangerous territory because of the because it's a highly nonlinear effect. You would definitely start to worry about like the exclusion of certain types of model or certain types of interaction variables in the model because of the way that Stepwise omits so many types of models. In particular, with interaction variables, we sort of by definition know that the effect is not linear. And so the worry about omitting kind of the correct one is probably really high with this type of approach.
Yeah, that makes sense. Thank you.
Yep.